Welcome back. So we find ourselves at the end of the chapter, and this is the part where we're gonna start relating thermodynamics to equilibrium. So what are we gonna do on this part of the chapter? We're gonna once more calculate the entropy, but we're gonna do it this time from standard molar entropies, which is nothing more than using the appendix at the end of the book and calculate it using products and reactants the way you know how to do already enthalpy. So we're gonna cover that again. So we're gonna also do the same procedure for the free energy or the Gibbs free energy using free energies of formation. Once we do that, we're gonna calculate the Gibbs free energy under non-standard conditions. So when you do it with the appendix, those are gonna be standard conditions. And then ultimately, we're gonna relate the Gibbs free energy with the equilibrium constant, bringing chapter 19, 18, 17, and 16 all together. So let's begin with the third law of thermodynamics. So the first law of thermodynamics, energy cannot be destroyed, energy cannot be created, energy can only be transformed. The second law, the entropy of the universe always tends toward increase or positive. And the third law of thermodynamics is that if we are absolute zero, and we talk about this several times during the class, if we happen to be at absolute zero Kelvin, the entropy is zero, because that means you have a solid, only one position, it cannot move. So your microstates are going to be equals to only one microstate. And when you do the natural logarithm of that, you get zero. And then multiply that by the Boltzmann constant, which is going to give you zero. So the only time you're going to have zero entropy is when you have zero movement at absolute zero on the Kelvin scale. So going back to standard entropy, we can calculate that using the appendix that is on the books, that give you the standard molar entropies that have been calculated or found doing experimentation. So we can use those to calculate entropy of a given chemical equation. And we already talked about that the entropy for gases is higher than the entropy for liquids or solids. We also saw that entropy increases with molar mass, because if you have molar mass, it means you have more atoms, and the atoms are bonded to other atoms, and each one of those bonds can do different movements, so you're going to have more entropy. So it definitely has to do with the number of atoms in a formula. And this is how we're going to use the standard molar entropies of formations to calculate the entropy of a system or a chemical reaction with a specific number, not just positive or negative. And this is the same way we used to do it with enthalpy. So we're doing entropy now. This is the same way we used to do it with enthalpy back on 1411 on our General Chemistry 1. Yeah, you obviously need a balanced chemical equation because you're going to use the coefficients of all the products minus the coefficients with the multiplied by the standard molar entropy of all the reactants. But before we do that, let's talk some more about the Gibbs free energy. And we start seeing how this is going to relate to equilibrium. If the Gibbs free energy is negative, we know that we're going to have a spontaneous reaction. However, if we happen to have an equilibrium, which reaction are we talking about? Left to right or right to left? There's two reactions there, right? So if it's negative, that means that it's going to be spontaneous on the forward reaction because K, or the equilibrium constant, is going to be bigger than Q. So if the equilibrium is out, out of synchronization, favoring the products, then it's gonna tend toward that. So that would be when delta G is less than 0. If it happens to be 0, that means that K equals Q. So it's already at equilibrium, so it's not going to tend toward the reactant or toward the products. If it happens to be positive, if delta G happens to be positive, then the reaction is non-spontaneous, but that's only from left to right. That means that the reaction is going to be spontaneous from right to left, the inverse reaction. So when you have an equilibrium, we know the reaction is happening because you have an equilibrium, right? It's given, the reaction is happening. There's an equilibrium. So spontaneity is going to be based on which direction. If it's spontaneous toward the products or if it's spontaneous toward the reactants. So in that case, it means that it's going to be, the reverse reaction is going to be spontaneous, which means Q is going to be bigger than K, therefore it's going to favor the reverse reaction. So all these concepts are going to be linked one way or another. And we calculate the standard Gibb free energy for a chemical reaction. For a chemical reaction, the same way we do the entropy and the enthalpy by using the thermodynamics value table on the index or the appendix and using the products. But before we start practicing with that, let's define them. So if we can find the standard Gibb free energy really easy by using the appendix, what happens when you don't have standard conditions? Well, that's given by this formula. Gibbs free energy at any condition is going to be equal to the one that you can find using the appendix, the Gibbs free energy standard conditions, plus the R constant, which is going to be the one that gives us energy, because we're dealing with energy, times the temperature of the system, times the natural logarithm of the Q. And you know what Q is. Products over reactants to their proper powers at initial conditions, when it's not in equilibrium. And for the purpose of standard conditions, we're gonna say that the molarity equals 1. And the Q is going to be 1 if we're talking about standard conditions. So standard condition, the Q is going to be equal 1 because all the concentrations have to be 1 molar, so they all are going to be the same. So if you have G equals G standards plus RT ln 1, then this becomes 0. 0, and G standard is going to be equals to minus RT ln K. So at the standard conditions, we have these terms drop because now we are dealing with equilibrium, which is what we have in here. Gibb free energy at standard condition is the same as minus RT ln K. So once more is a quick summary. At equilibrium, Q is going to be equals to K. Therefore, the Gibb free energy total value is going to be 0, which means you can say that the G standard is going to be equals to minus RT ln K. And if you do that, you can use your algebra to find your K. So this is an excellent way to find an equilibrium constant if you can calculate delta G standard and you know the temperature. So basically what I'm telling you is you can also find the equilibrium constant using the appendix. So all those thermodynamic values that we have on the appendix are now allowing us to find indirectly the equilibrium constant. Find the delta G, and then you can solve for the equilibrium constant. So let's do our first problem. Calculate the entropy of the reaction given these values. So how are we going to do this? We're going to do delta S of the reaction is going to be equal to the sum of the multiplication of the coefficient times the delta S of the products minus the sum of the multiplication of the coefficient times the delta S of the reactants. So in this case, we're going to have ethane, C2H6. C2H6 is going to be, and it's a gas, make sure you pay attention to that. And super important, make sure that you pick the right column. So that's not what we're looking for. That's not what we're looking for. We're looking for entropy. Make sure you pick the right column. So it's going to be 229.2 joules over moles Kelvin. It's the molar entropy, 229.2. So that's going to be delta S of the reaction is going to be 229.2 joules moles kelvins. The coefficient is 1 times 1. It's the only product minus C2H4 ethene, C2H4 gas is going to be 219.3 minus, and it's only one of them, 219.3 joules moles kelvins plus, that's what this means, plus hydrogen, and hydrogen gas is going to be, we're looking at the entropy, 130.7. And there's only one of them, 130.7 joules moles Kelvin. So when we do that, all we're doing is $229.2. Get my calculator here quick. $229.2 minus 219.3 minus 130.7, which is going to be delta S of the reaction is going to be minus 120.8 joules moles Kelvin. So this is going to be a reaction that is going to tend not to be spontaneous because we got a negative entropy. So by looking at the reaction itself, can we rationalize that value? We got a negative value. Well, let's see. We began with 1, 2 gas molecules becoming one molecule, so it became more organized. So yes, it makes sense that, that this gave us a negative value. So that's how we do, that's how we find the entropy of a system or a chemical reaction in this case by using the entropy of formation of each one of the components. Always products minus reactants multiplying by their coefficients. The main problem I have seen the students having with this type of problem is that they tend to use the wrong column. So make sure you're looking at the heading of the columns. So you should be able to do those two now using the appendix 2B on your book, and it's also on the packet that is posted on Canvas. And if by any reason you don't find any of the some of these substances on the packet or on the book, go find it on the internet. But make sure that the units are the same. What about this one here? This one is asking us to calculate the enthalpy, the entropy, and the delta G at 25 degrees Celsius. And then determine if the reaction is going to be spontaneous or not. And if the reaction happens to be not spontaneous, indicate if a change in temperature will make it spontaneous or not. Well, let's see. What would be delta H? So we got the column here. So NO2 gas is 33.2. So the product, 33.2 kilojoules per mole. And there's two of them. Minus the reactant, there's only one reactant, and there's only one of them. And according to the table, it's a gas, so make sure you pay attention to the phase. So make sure you pick up the gas. 9.16. Gonna be 9.16. So our delta H is gonna be 2 times 33.2 minus 1 times 9.16, which is going to be 57.24. These are kilojoules per mole, and these are kilojoules per mole. So based on the delta H, there's a possibility that this reaction is it's an endothermic reaction, so it's a possibility that it may not happen, but we don't know for sure until we calculate the delta G. So delta H is going to equal 57.24 kilojoules per mole. Let's calculate the entropy the same way we did before. So the entropy is going to be, once more, the product, which is two of them, multiplied by 240.1. And these are going to be joules, not kilojoules. These are going to be joules, moles, Kelvin, minus the reactant. There's only one of them, and the value is going to be for the gas, 304.4 joules, moles, Kelvin, and this is going to give me 2 times 240.1 minus 304.4. That's going to be 175.8 joules moles Kelvin. So the entropy of the reaction is going to be 175.8 joules moles Kelvin. And what about delta G? Delta G is standard because we're using the appendix, which is all based on standard formation. It's going to be the product, which is two of them. And delta G is going to be 51.3. And that's going to be kilojoules per mole. Minus the reactant, which is only one. And it's the gas, 99.8 kilojoules per mole. So our delta G is going to be 2 times 51.3 minus 99.8, which is going to be 2.8 kilojoules per mole. So delta G is going to be 2.8 kilojoules per mole. So now that we have all the calculations, we can start making sense out of this. So the question now is whether the reaction is spontaneous or not. Well, delta G is positive, so the reaction is non-spontaneous. So to be spontaneous, delta G has to be negative. Delta G equals 0, that means it's at equilibrium. So this will be a non-spontaneous reaction because our delta G was positive. If the reaction is non-spontaneous, like ours is, indicate whether a change in temperature will make it spontaneous. What does that mean? Well, how can we relate temperature to spontaneity? We can only relate it this way. Delta G equals delta H minus T delta S. So we know that is 2.8 at 25 degrees Celsius. So if we change the temperature, we know that if we change the temperature, we change the rate and all that kind of stuff, right? So if we change the temperature, can we make it spontaneous? Well, let's see. Delta G is going to be equals to 57.24 kilojoules per mole minus a temperature times the entropy, which is going to be 0.176 kilojoules. All I did, I just changed it to kilojoules per mole Kelvin. And we want to see if changing the temperature is going to make it spontaneous or not. Well, here's the deal. It's going to have to be negative. So this is positive. All this here is negative. So this number has to be bigger. If we can make this number bigger because it's negative, then that will make delta G negative and that would be spontaneous. So a change in temperature can make it spontaneous. So if this is the temperature was 100 Kelvin, that will make it 17.6 kilojoules, which still gives us a positive number when we do the subtraction. But what about if the temperature was 1000 Kelvin, for example? If it was 1000 Kelvin, then this will become 176 kilojoules, and that will give us a negative value. So this reaction can be spontaneous at very, very high temperatures. So if you're working for a company that is focused on bringing down their carbon footprint, they need to save energy. And if you propose this reaction to them, they're going to say, no. Unless this reaction is producing something very, very, very valuable, we're not going to do it because we have to spend a lot of energy. The temperature has to be too high for this to work. So for those of you with engineering minds, that's the kind of stuff you need to be thinking about. How can I control my reactions by knowing these thermodynamic concepts? So this reaction will only happen at very, very, very high temperature, which are going to consume a lot of energy, and therefore they're going to bring down the bottom line, which is the profit for the company. But if you're thinking about the environment, you don't want to do this either, because this will not be good for the environment, because it's an excessive amount of energy that is going to be used. So with that in mind, you should be able to work on those two problems. And now let's do something else. So we have a different reaction now. And we want to calculate the delta G, not the delta G standard, the delta G. So delta G equals delta G standard plus RT ln Q. That's the formula that we use, where Q is the products over the reactants at the respective powers at initial conditions. So how can we calculate this? Temperature is going to be 25 degrees Celsius. So temperature is 298 Kelvin. This is 8.31 joules moles Kelvin. Delta G, we can find it on the tables, right? So we can find delta G on the tables. We know our R, we know our T. So the only thing we need to plug in is our Q. And our Q is going to be, well, we're doing pressures on this case. Our Q is going to be the pressure of hydrogen to the square times the pressure of carbon monoxide divided over the pressure of methanol. And that's going to be our K expression, but we are not dealing with equilibrium pressure, so that's going to be our Q. And this will go there, this will go here, and that will go there. And that's all you have to do. Once you have done that, it's just a math problem. Plug those numbers on your calculator and get the answer. You know how to find delta G using the appendix. We just practiced that. Make sure you use the right value for R, because we're dealing with energy. And make sure you change the temperature to Kelvin. And that should give us our delta G. So with that in mind, you should be able to do that. And we can move to this problem now. So consider this reaction, and there's a equilibrium constant. So this is actually an equilibrium, right? So we have an equilibrium constant, so it should be an equilibrium. Calculate delta G of the reaction for the reaction at 25 degrees Celsius under each condition. Well, let's start with delta G. Delta G of the reaction equals delta G standard plus RT, L, and Q. And we're going to do the first one at standard conditions. At the standard conditions, that means all our concentrations or pressures are going to be 1. So this becomes, that becomes, sorry. So the Q, becomes 1, which means ln Q equals 0, which means delta G of the reaction equals delta G standard. And we know that delta G standard equals minus RT ln Q. So standard conditions, you can just go to the appendix and find the delta G standard. That's what that's saying. So we know how to do the first one. What about at equilibrium? At equilibrium, delta G equals delta G standard plus RT ln Q. At equilibrium, delta G equals 0. So we can say that delta G is going to equals minus RT ln Q. And since we're talking about equilibrium, there's no such thing as Q. At equilibrium, this is K. So delta G standard, which is going to be our delta G now, is going to be equals to minus 8.31 joules moles Kelvin (298 Kelvin for the temperature), ln K, which is going to be 2.26 times 10 to the 4. So when you do that calculation, you get your delta G, which we know is going to be a negative value, therefore spontaneous, which we know it is because it's at equilibrium. So it's happening. And what about the last one? The last one is similar to the one we did before. So you know that the reaction is happening. The reaction is happening at 25 degrees Celsius. Delta G equals delta G standard plus RT ln Q. Q is going to be the pressure of methanol to the power of 1 divided by the pressure of carbon monoxide times the pressure of hydrogen gas to the square. We have all these pressures in there, so you can plug that in there. That's going to be our Q. T is 298, right? 25 degrees Celsius. R is 8.31. And you already found delta G on the first part. So you can use that and you get your delta G. So nothing more, this problem is doing nothing more than relating now how delta G relates to an equilibrium constant. And the main formula that we used here was delta G standard equals minus RT ln K. On this case, we have the K, so we can find the delta G. And then you can compare that with the appendix method if you want to. So with that said, you should be able to do that. Do that. And at that point, we should be able to find that. And remember, I showed you also how to find the K value So if you give in the delta G, you can find the equilibrium constant that way. So that brings us to the end of the chapter, where we just discussed how to find the entropy changes using the standard molar entropies given on the appendix. You can do the same thing with the Gibb free energy. We saw how to calculate delta G under non-standard conditions. Delta G equals delta G standard plus RT ln Q. You know how to do Q already. And then we saw how we can relate Gibb free energy or delta G to the equilibrium constant, where we have delta G standard equals minus RT ln K. So several ways now for you, or at least one more way, to find the equilibrium constant. And with that, we can close the chapter where we talk about the second law of thermodynamics, the third law of thermodynamics. We talk about what a spontaneous process is, reversible and irreversible, based on the entropy. We know how to deal when the temperature is constant. We defined entropy. We saw how the entropy relates to microstates and the Boltzmann constant. We saw how entropy can be figured out by looking at the structure and seeing how many atoms, how big the molecule is, looking at the Lewis structures and the shape and see the different type of movement that the molecule can do. The more possibilities of movement, the higher the entropy. So we saw how the entropy of the surrounding relates to the heat and the temperature, and at the same time with the enthalpy. We got a good way of looking at the chemical equation and decided if the entropy was positive or negative by looking at the states and the amount of molecules. We know that delta G less than 0 is going to be a spontaneous reaction. But if an equilibrium is involved, we have to be talking about a spontaneous on the forward way or a spontaneous on the reverse way. We saw how by using delta G equals delta H minus T delta S, we can relate temperature to the spontaneity of the reaction, and we can say this reaction can happen only at high temperatures, or this reaction can happen only at very low temperatures. And then we saw how we can calculate delta G from that, just what I said, from the enthalpy and the entropy, and then everything else that we just did. And with that, we bring this chapter to a closing, which brings us closer to the end. We got 2 more chapters to go, and we will be done with this course. So keep having fun. See you soon. Take care.